Welcome to video 4.3 in our first principles of astrophotography series. In this video, we discuss the particle nature of light, that is, photons, which are essential to the operation of camera sensors and to the understanding of emission nebulae.
What do you call a photon that flies a plane?
Captain Photon.
Wrong. A pilot light.
This video is based on section 4.3 of our first principles of astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. All right, principle 51, photon energy. The energy of a photon of frequency nu is E equals h nu, where h is Planck's constant. So the most energetic photons are those with high frequencies and short wavelengths. Energies are measured in joules or electron volts, where 1 electron volt equals 1.6 times 10 to the minus 19th joule.
So first of all, this is Planck's constant. It's a fundamental constant of nature. It's the most important constant that deals with the physics of the very small, which is what we call quantum physics. It's an extremely small number. So I don't know if you saw here that we're talking about 10 to the minus 34.
Put that in the millions and billions for me.
Yeah, so a billion is 10 to the minus, a billionth is 10 to the minus 9. A billionth of a billionth is 10 to the minus 18. A billionth of a billionth of a billionth is 10 to the minus 27.
Getting closer.
And a billionth of a billionth of a billionth of a billionth is 10 to the minus 35. So we're pretty much there. So it's a billionth of a billionth of a billionth of a billionth of a joule second. Yeah. So a joule is the normal.
So small.
It's so small, and it's such an important part of physics to really understand what's happening on the very, very smallest scales. So a joule is a measure of energy that, you can measure, if you throw a baseball, the kinetic energy of the baseball will be measured in a few joules, depending on how fast you throw it.
Okay.
But when you're talking about very, very small things, which we will be, we're talking about electrons, we're talking about photons, the energies that you're going to be dealing with are really, really small. So joules just isn't very convenient, and we use a unit of energy called the EV, which is 10 to the minus 19 joules, which is a billionth of a billionth, and roughly a billionth of a joule.
So there's a lot of EVs in one electric vehicle, EV.
There's a lot of EVs in one EV. Yeah, that's right. Yeah, I hadn't thought of that. It's very, very good. So this, I can't stress how important this is, both in astrophotography and in physics. The energy of a photon. This is a particular packet of light. So a lot of times it's denoted as just a kind of a squiggly line. Light can be thought of as either, and sometimes behaves as, a regular wave, like you would see on a water wave. But in many other instances, light behaves as a particle, and we'll give evidence of that. In fact, that evidence is the photoelectric effect, which is what Albert Einstein got his Nobel Prize for.
Good.
But the important fact here is that the energy of a photon depends on the frequency of that photon, which is the frequency of the light that is carried by that photon. And that's measured, as we talked about in a previous video. Nu, this is the Greek letter nu, and it's the frequency. And it's measured in units of hertz, Hz. So what this equation says, E equals h nu, is that the energy of the photon is proportional to its frequency. The higher the frequency, of the photon, the greater the energy that's carried by that photon. Why is that important? You don't want to get hit with a gamma ray photon. That's going to be bad for you. Just like Ghostbusters crossing the streams, you don't want to get hit with much gamma ray radiation because that's going to do a lot of damage.
Unless you want to become the Hulk.
Yes, that would be a good idea.
Yeah.
Okay, so remember E equals h nu. As the frequency gets big, the energy of the photon gets big. And this is the increasing frequency. So long radio waves have very low frequencies, like 1 cycle per second. 10 to the 0 is 1. So it's going back and forth only 1 time per second. But when you're talking about gamma rays, which are even more energetic than X-rays, which everybody knows are dangerous, gamma rays are much more dangerous. That's why they use gamma rays as a gamma knife. So you can use surgery using gamma rays to cut human flesh. But its frequency is around 10 to the 24 hertz, cycles per second. So it's 10 to the 24 times more damaging and more energetic than long radio waves. So these are the dangerous high energy electromagnetic radiation. And this is not dangerous. Certainly ultraviolet radiation, I think everybody pretty much knows that the sun's ultraviolet radiation hitting your skin does nasty things to you. It gives you cancer, it gives you sunburn, et cetera, et cetera. X-rays even more dangerous, and then gamma rays even more than that. Infrared is just heat, and you can't see infrared radiation, but if you hold up you can feel it. You can feel infrared radiation from the sun. That's which warms you up on a sunny day. Or sometimes if you have a pan you're cooking eggs on, for example, and you turn it sideways, you can feel the heat directly propagating at the speed of light, which is infrared radiation. Okay, that's a review of 1 electron volt. And remember, we haven't said this yet, but electron volt, a lot of people get confused between that and a volt. It's not a volt. It's not a measure of voltage at all. It's a measure of energy. So let's talk about the visible photon energy. We worked out in a previous video the frequency associated with the average visible wavelength, and we got a frequency of 5.4 times 10 to the 14 hertz. Planck's constant is 6.6 times 10 to the minus 34. That's an extremely small number that does your quantum mechanics for you. And that gives you an answer in joules. Hertz is measured in cycles per second, so the seconds here cancel this, and we end up with joules. A cycle is not really a unit, so we end up with this in joules, and then we convert from joules to EV. We get 2.3 EV. So what this little exercise says is that the EV, or electron volt, is a useful measure of energy for visible frequencies, right? It's a number that's around 1, right? Which makes sense for doing that.
This is going to come into astrophotography sometime, right?
That's a great question. Yes. In order to understand the spectroscopic lines in hydrogen and oxygen and sulfur, which is covered later in this chapter, we're going to need to have to address these energies, these energy levels of atoms, which are generally measured in EV.
Okay, so don't fall asleep for this part. It'll come in later.
Yeah. Okay, thanks for that, Ren.
You're welcome.
All right. Principle
52, photon energy. Take 2. The energy of a photon of spectroscopic wave number nu. Hang on.
Tilde.
Nu tilde equals, it's not Matilda, it's nu tilde, equals 1 over lambda is E equals HC nu tilde.
So this little squiggle is a symbol that we use in physics called the tilde. I think there's even one in the upper left-hand corner of your keyboard. For sure there is one up there. Anyway, nu tilde is the so-called spectroscopic wave number. And that's important. The chemists like to do weird things with their wave number. It's called a wave number. And it's defined just simply as 1 over the wavelength. Wavelength is measured in meters, as we learned in a previous video. The peak-to-peak distance in a wave is called the wavelength. It's measured in meters, no big deal. And so if you take 1 over something measured in meters, you're going to get something measured in 1 over meters. The units are 1 over meters. So the units of nu tilde are inverse meters. And we'll use this when we're talking about spectroscopy. If you take then E equals h nu, and then you recall, remember this equation, C equals nu times lambda. This is the speed of light. This is the frequency of light, and that's the wavelength of light.
Okay.
If you solve that equation for nu by dividing both sides of the equation by lambda, you get nu is C divided by lambda.
Right.
And then if you substitute that into here, then we end up with E equals h. And nu, we just showed us C over lambda. And let me just write this in a slightly more provocative way.
Oh.
So it's hc times 1 over lambda. But 1 over lambda is defined as the spectroscopic wave number nu tilde.
Great.
And that's this equation right here. That's how that relates to this more standard style. This is typically used in physics. And this form is often used in chemistry and spectroscopy.
So we're going to work more with nu tilde, right?
We'll work with both. Most of what we'll do is with just regular old nu. So
Okay. So we maybe won't go waltzing nu tilde.
it's spoken by somebody who spent 2 years in Australia.
Yeah.
I think that's the national anthem or national song or something like that. Waltzing nu tilde.
Yeah.
It kind of sounds like Nutella, really, the hazelnut spread, which makes me hungry right now.
With some pretzels.
Yeah.
So good.
So Einstein did not get the Nobel Prize for the special theory of relativity, which is what he's most famous for. What he did get the Nobel Prize for is the photoelectric effect, and he got that Nobel Prize in 1905. He predicted that when light hits a surface, then it can kick electrons off of that surface. So these two squiggly lines represent photons. They hit this surface. So this is a solid. Like, for example, zinc, what we do in a physics demo, and you can look up in physics demos where we actually do this demo. Physics Demos is my YouTube channel. Yeah. So what happens is these photons come down and they hit these red, the electrons are denoted by these red spheres. And these photons are capable of kicking those spheres out of the solid, which basically charges the solid. If you remove a negative electron, then you're going to end up with a solid that's positively charged.
Right.
And that was verified that electrons can be kicked off of a surface of a solid by a photon. That's called the photoelectric effect.
You might say the photoelectric effect is the liberation of electrons from a surface by photons that strike the surface.
I might say that.
You're welcome.
And why is the photoelectric effect important in astrophotography? Do you know the answer?
Because of the sensors. That's how it gets
Exactly.
onto the sensor.
That's how a sensor works. You have a sensor, and we're going to talk about sensors in the next chapter. You have a sensor that detects incoming photons through the photoelectric effect. Those photons come in, hit a photosite on the sensor, liberate electrons, and those electrons are captured in a little well with a well capacity usually around, for our camera, it's around 50,000 electrons. So you got these little electrons in this little well that have been kicked off of the surface. It's so cute. It's just darling. Yeah. And that's how your sensor works. So, Merry Christmas.
Almost. We're getting close.
Thanks for watching.
And we'll see you next time.